Hello there, and welcome to the Sleepless Scientist. Tonight, we're traveling far beyond the familiar constellations, past the edge of everything we can see with our naked eyes, to a place where a cosmic phoenix burns in the dark. It's a galaxy cluster so powerful, so impossibly bright, that it challenges everything we thought we knew about how the universe works. A place where black holes feed, stars are born from destruction, and ancient light tells stories from billions of years ago. So settle in, let your mind drift outward, and let's journey together to Phoenix A. And just before we begin, if these calm, curious explorations help you unwind, or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. The story of a cosmic phoenix. There's an old legend, told across many cultures, of a bird that never truly dies. The phoenix. It burns, collapses into ash, and then rises again, reborn from its own embers. It's a story about cycles, about endings that become beginnings. And strangely enough, the universe has its own version of this myth. Deep in the southern sky, there's a galaxy cluster named Phoenix A. It glows with the light of trillions of suns. At its heart lies a black hole so massive, so active, that it devours matter and spews out energy in cosmic jets that stretch across unimaginable distances. And yet, from that destruction, new stars are born. The cluster cools, collapses, and ignites again. It's a cycle of death and rebirth on a scale we can barely comprehend. The ancient storytellers never saw this place, but somehow they understood the pattern. That fire and renewal are woven into the fabric of existence itself. The firebird of the universe. Imagine a bird made entirely of light and energy, wings stretching across millions of light years, feathers glowing with X-rays and radio waves. That's Phoenix A. Not a creature, of course, but a galaxy cluster that behaves like one. It radiates power. It sheds energy in vast plumes that ripple through space like the beat of celestial wings. Astronomers chose the name carefully. Phoenix, a symbol of resurrection, because this cluster doesn't just exist. It transforms. It takes cold gas and heats it. It takes dying matter and turns it into newborn stars. It collapses under its own gravity, then erupts again in bursts of light and sound. It's a firebird that never rests, never fades, never truly dies. And every time we look at it, we see another chapter in its endless story. A reminder that even in the vast, cold silence of space, there are places that burn with life. The cluster, hidden in the southern sky. If you live in the northern hemisphere, you'll never see Phoenix A with your own eyes. It hides below the horizon, nestled in the constellation Phoenix, a grouping of faint stars that ancient mariners once used to navigate the southern seas. The constellation itself is subtle, easy to miss, but what lies within it is anything but. Phoenix A sits billions of light years away, invisible to even the most powerful optical telescopes on a casual glance. It doesn't announce itself with bright stars or colorful nebulae. Instead, it whispers in wavelengths our eyes can't see. X-rays, radio waves, infrared glow. It took specialized instruments, pointed with precision, to pull its story from the darkness. And when astronomers finally found it, they realized they were looking at something extraordinary. A titan, a colossus, a galaxy cluster that rewrites the rules, all hidden quietly in a corner of the southern sky. The discovery of Phoenix A. The story of Phoenix A begins not with a single moment, but with a slow unveiling. In the late 20th century, astronomers were scanning the skies with radio telescopes, searching for distant signals. And there, in the constellation Phoenix, they detected something unusual, a powerful radio source, pulsing with energy. At first it seemed like just another distant galaxy, but as more data came in, the picture grew stranger. X-ray observatories like Chandra pointed their mirrors at the same spot. What they saw was astonishing. A massive galaxy cluster, glowing with superheated gas, wrapped around a central galaxy of almost unimaginable brightness. The more they looked, the more they found. Jets of matter, bubbles of energy, star formation happening at breakneck speed. Phoenix A wasn't just another cluster. It was an outlier, an extreme, a cosmic laboratory where the universe was doing things it wasn't supposed to do, and the astronomers who found it knew they'd stumbled onto something truly remarkable. The astronomers who found the giant, the discovery of Phoenix A, wasn't the work of one person or one night. It was a collaboration across decades, across continents, across wavelengths of light. Radio astronomers laid the groundwork, detecting the faint hum of energy from the cluster's core. X-ray astronomers followed, using satellites like Chandra and XMM Newton to map the hot gas that fills the space between galaxies. Optical telescopes like Hubble peered through the glow to find the stars beneath, and infrared observatories like Spitzer revealed the dust and the newborn suns hidden within. Each team added a piece to the puzzle. Each observation refined the picture, and slowly, the giant emerged from the noise. These astronomers didn't just find a cluster, they found a phenomenon, a place where theory and reality collided, where black holes, galaxies, and star formation all danced together in ways no one predicted. Their work turned Phoenix A into one of the most studied objects in the distant universe, a beacon, a mystery, a gift to science, the galaxy that defied expectations. There are rules in astrophysics, not laws written in stone, but patterns we've observed over and over. Galaxies grow slowly, black holes feed steadily, star formation happens in bursts, then fades. But Phoenix A didn't follow the script. At its center sits a galaxy forming stars at a rate that should be impossible for something so massive. Thousands of new suns every year, born from gas that should have stayed too hot to collapse. The black hole at its core is feeding at a rate that defies the usual limits. And instead of tearing the cluster apart with its energy, it's somehow regulating it, keeping things in balance, creating and destroying in perfect rhythm. Astronomers call this an outlier, a statistical anomaly, but maybe it's something else. Maybe it's a reminder that the universe is wilder, stranger, and more creative than any model we build. Phoenix A doesn't defy expectations. It expands them. The Phoenix cluster awakens. For billions of years, Phoenix A slept, or at least, that's how we imagine it. A cluster of galaxies, bound together by gravity, drifting through the expanding universe, gas cooling between them, stars aging quietly. And then, something changed. Maybe two galaxies collided at the center. Maybe the central black hole found a fresh supply of fuel. Whatever the trigger, Phoenix A woke up. The black hole began to feed. Jets of energy erupted from its poles. The gas that had been cooling suddenly reheated, glowing in X-rays. Sound waves rippled outward, carving cavities in the surrounding plasma. And in the wake of all that chaos, stars began to form. Not just a few, thousands. It was an awakening on a cosmic scale, a quiet giant suddenly roaring to life, and it's still going. Right now, as you listen to these words, Phoenix A is burning, radiating, transforming, a firebird in flight, the heart of a vast cosmic web. Phoenix A doesn't float alone in the void. It sits at the intersection of something much larger, a cosmic web. Imagine the universe as a vast tapestry, woven from invisible threads of dark matter. Along those threads, galaxies cluster like beads on a string, and at the nodes, where the threads cross, you find the giants. Phoenix A is one of those nodes, a hub, a gravitational anchor for hundreds of galaxies, all bound together by forces we can't see but can measure. The web stretches for hundreds of millions of light years in every direction, connecting Phoenix A to other clusters, other superclusters, in a vast network that spans the observable universe. It's easy to think of galaxies as islands, but they're not. They're connected, part of a structure so large, so intricate, that we're only just beginning to map it. And Phoenix A is a bright, burning knot at the center of it all, the brightest galaxy in its realm. In the heart of Phoenix A, there's a galaxy, not just any galaxy, but the brightest one in the entire cluster. Astronomers call it the brightest cluster galaxy, or BCG. It's a giant elliptical galaxy, bloated with ancient stars, sitting at the gravitational center of everything. But brightness here doesn't just mean starlight. It means X-rays. It means the glow of superheated gas. It means the radiation pouring out from the supermassive black hole at its core. This galaxy outshines all its neighbors combined. It dominates the cluster, not just with light, but with gravity, pulling in gas and smaller galaxies, growing larger over time. It's the queen of the Phoenix cluster, the central flame around which everything else orbits. And it's still shining, still feeding, still growing, a beacon in the dark, visible across billions of light years. The brightest light in a realm of shadows. The enormous glow of hot gas. Between the galaxies of Phoenix A, there's something most people wouldn't expect. Gas. Not the cold, dark hydrogen of empty space, but superheated plasma, glowing at temperatures of tens of millions of degrees. This gas fills the space between galaxies like an invisible ocean held in place by the cluster's gravity. And it glows, not in visible light, but in X-rays. When astronomers point X-ray telescopes at Phoenix A, they don't see individual galaxies. They see a vast glowing halo of hot gas, brighter than almost anything else in the universe. This gas is the lifeblood of the cluster. It's where stars are born. It's what the black hole feeds on. It's the medium through which energy flows. And it's enormous, stretching for millions of light years, containing more mass than all the stars in all the galaxies combined. A silent ocean, burning bright, holding the cluster together. The X-rays that revealed its power. We owe our understanding of Phoenix A to X-rays. Before X-ray astronomy, we couldn't see the full picture. Optical telescopes showed us galaxies. Sure, but they missed the real story. The story written in heat, in energy, in the glow of plasma heated to unimaginable temperatures. When the Chandra X-ray Observatory turned its gaze toward Phoenix A, it revealed a sight no one had seen before, a cluster glowing so brightly in X-rays that it rivaled the most energetic objects in the universe. The gas between the galaxies was radiating energy at a staggering rate, and at the center, where the brightest galaxy sat, there was a point source, a concentrated node of X-ray emission, the black hole. Without X-rays, Phoenix A would have remained a mystery, a footnote, but with them, it became a revelation, a window into the most extreme processes the cosmos has to offer, the central black hole that rules it all. At the very heart of Phoenix A, buried deep within the brightest cluster galaxy, there's a black hole, but calling it a black hole almost feels inadequate. It's a supermassive black hole, weighing in at billions of times the mass of our sun, and it's active, ferociously active. This black hole is feeding on the gas around it, pulling it in with irresistible gravity, heating it to millions of degrees before it crosses the event horizon. And as it feeds, it radiates. Not light from the black hole itself, nothing escapes from there, but from the swirling disk of matter around it, glowing so brightly it outshines entire galaxies. This black hole doesn't just exist, it rules. It shapes the cluster, it heats the gas, it launches jets of energy that carve the space around it. Everything in Phoenix A, from the galaxies to the stars to the cosmic web itself, exists in the shadow of this monster, the most energetic object in the known universe. For a time, Phoenix A held a title, the most energetic object in the known universe. Not the most massive, not the brightest in optical light, but the most energetic. The amount of energy pouring out of the central black hole and the surrounding gas was almost incomprehensible. More energy than entire galaxies produce. More than the combined light of 1 trillion stars. This energy comes from gravity, from matter falling into the black hole, converting its mass into radiation with terrifying efficiency. It comes from the hot gas cooling and collapsing, releasing energy as it does. It's a furnace on a cosmic scale, burning with a fury that echoes across the universe. Even now, as new observations refine our measurements, Phoenix A remains near the top of the list, a monument to the raw power the cosmos can unleash when gravity, matter, and time collide. The monster at the core. The black hole at the center of Phoenix A isn't just large. It's a monster, a cosmic predator, devouring everything that comes too close. Gas spirals into it, heating as it falls, glowing with X-rays and gamma rays. Stars that wander too near are torn apart by tidal forces, their matter stretched into long streams that feed the beast. And all the while, the black hole grows. It's been growing for billions of years, consuming galaxy after galaxy, black hole after black hole, merging and expanding with each meal. It's not malicious, of course. Black holes don't have intent, but they have hunger, an endless gravitational pull that nothing can resist. And in Phoenix A, that hunger has shaped everything. The galaxies orbit around it. The gas flows toward it. The entire cluster exists in its thrall. A monster at the core, silent and unseen, ruling an empire of light, the jets of matter and light. But the black hole doesn't just consume, it also creates. From the poles of the spinning black hole, twin jets erupt, streams of matter and energy, accelerated to nearly the speed of light, shooting out in opposite directions. These jets are unlike anything else in nature. They're made of charged particles, electrons, protons, spiraling along magnetic field lines, radiating as they go. They glow in radio waves and X-rays, visible from billions of light years away, and they're powerful. These jets plow through the surrounding gas, carving enormous cavities, bubbles of space where the gas has been pushed aside. They heat the cluster, preventing the gas from cooling too much, regulating star formation, balancing the system. The jets are the black hole's signature, its presence made visible, a reminder that even the darkest objects in the universe can shine. The feeding of a cosmic giant. How does a black hole grow so large? How does it feed? The answer lies in the gas around it. Phoenix A's central black hole sits in a vast reservoir of hot plasma, slowly cooling, slowly falling inward. As the gas cools, it becomes denser, more susceptible to gravity's pull. It spirals in, forming an accretion disk around the black hole. And as it spirals, it heats up, glowing brighter and brighter until it's radiating more energy than entire galaxies. Some of that gas crosses the event horizon, lost forever, but much of it is blown back out by the black hole's jets, reheating the cluster, starting the cycle over again. It's a delicate balance. Too much feeding, and the black hole could consume everything, leaving the cluster cold and dead. Too little, and star formation would run wild, depleting the gas reserves. But Phoenix A has found equilibrium, a cosmic giant, feeding just enough to stay alive. The black hole that creates and destroys. There's a paradox at the heart of Phoenix A. The black hole destroys. It consumes gas, tears apart stars, swallows light itself, but it also creates. The energy it releases prevents the cluster from collapsing entirely. The jets it launches carve out space where new stars can form. The heat it generates keeps the gas in motion, stirring the cosmic ocean, ensuring that matter stays dynamic rather than static. In a strange way, the black hole is both predator and gardener. It culls the weak, but it also nurtures the strong. It takes, but it also gives, Astronomers call this feedback, a loop where destruction fuels creation, where endings become beginnings, and Phoenix A is the clearest example we have of this process in action. A place where the most destructive force in the universe is also, paradoxically, a source of life, the balance between growth and collapse. Phoenix A exists on a knife's edge. On one side, there's collapse. The gas between galaxies is cooling, growing denser, pulled inward by gravity. If nothing stopped it, the entire cluster would collapse into the center, forming an impossibly massive galaxy, perhaps even merging into a single monstrous black hole. On the other side, there's growth, star formation, the birth of new suns from cooling gas. But too much star formation would deplete the gas too quickly, leaving nothing behind but old dying stars. Phoenix A balances these extremes. The black hole's jets heat the gas, preventing total collapse, but enough gas cools anyway to fuel star formation. It's a tightrope walk, performed on a cosmic scale, over billions of years, and somehow, Phoenix A maintains its balance, growing, yes, but not collapsing, feeding, but not starving, a giant walking the line between creation and destruction, the cooling flows of the cluster. Let's talk about cooling in the space between galaxies. The gas is hot, millions of degrees, but even at those temperatures, it radiates energy. Slowly, over time, it cools, and as it cools, it contracts, growing denser, pulling more gas inward. Astronomers call this a cooling flow. For years, they expected to find these flows at the centers of all massive galaxy clusters, gas cooling, collapsing, forming stars at incredible rates. But when they looked, they found something strange. Most clusters weren't forming stars as fast as they should. Something was heating the gas back up, stopping the flow. The culprit, supermassive black holes. Their jets pump energy back into the gas, reheating it, balancing the cooling. But Phoenix A is different. The cooling flow here isn't entirely stopped. It's regulated, yes, but not halted. And that's why Phoenix A is so special. It's one of the few places where cooling and heating are in near-perfect balance. The birth of new stars from old heat. Out of the chaos, new stars are born. At the center of Phoenix A, in the brightest cluster galaxy, thousands of stars are forming every year. This isn't supposed to happen. Massive elliptical galaxies, like the one at Phoenix A's core, are usually dead, filled with old red stars, long past their prime. But here, the gas is cooling just enough, condensing into pockets, dense enough for gravity to take hold. And once gravity starts, star formation follows. These are young stars, blue and hot, burning fiercely. They light up the center of the galaxy, glowing in ultraviolet and optical light, visible even through the dust that surrounds them. It's a starburst, a sudden violent explosion of star formation, fueled by the very heat that should have prevented it. Old heat, cycled through the cluster by the black hole's jets, cooling just enough to collapse, creating new suns from ancient energy, a cosmic recycling program, billions of years in the making. The starburst at the center. At the heart of Phoenix A's brightest galaxy, there's a starburst. Not a single star, but thousands, tens of thousands, being born all at once. The center of the galaxy glows blue, the signature of young, massive stars. These stars are born from the cooling gas, collapsing under their own gravity, igniting fusion in their cores. They're short-lived, burning hot and fast, living only a few million years before exploding as supernovae. But in that brief time, they light up the galaxy. They inject energy back into the gas. They create heavy elements, carbon, oxygen, iron, that will become part of the next generation of stars. The starburst is a fleeting phase, a moment in the life of the galaxy, but it's a critical one. It's proof that even the oldest, most massive galaxies can be reborn, that the phoenix metaphor isn't just poetic, it's literal. The galaxy that shouldn't exist. By all rights, Phoenix A's central galaxy shouldn't be forming stars. It's too massive, too old, too hot. The gas around it should be too energetic to collapse. And yet, there it is, glowing with the light of newborn suns, defying expectations, rewriting the rules. Astronomers have spent years trying to understand it. How does a galaxy like this, in a cluster like this, manage to form stars? The answer seems to lie in the balance. The black hole heats the gas, yes, but not uniformly. There are pockets, filaments of cooler, denser gas that slip through the cracks, condensing into stars before the heat can stop them. It's a delicate process, easily disrupted, and yet Phoenix A maintains it, year after year, millennium after millennium. A galaxy that shouldn't exist, but does. A cosmic miracle, playing out in real time, billions of light years away. The mystery of its rapid formation. One of the biggest questions about Phoenix A is, how did it get this way so fast? Galaxy clusters take billions of years to form. They grow slowly, accumulating galaxies over time, building up mass through countless mergers and collisions. But Phoenix A seems different. Its central galaxy is forming stars at a rate that suggests rapid, recent growth. The black hole is feeding furiously, as if it just found a new supply of fuel. The entire cluster radiates energy, as if it's in the middle of a cosmic growth spurt. So what happened? Did two massive clusters collide, triggering this burst of activity? Did the black hole swallow a companion, doubling its mass overnight? Or is this just how some clusters evolve, and we're lucky enough to catch Phoenix A at a particularly active moment? We don't know yet, but the mystery makes Phoenix A all the more fascinating. A snapshot of cosmic evolution, frozen in time, the dance of gravity and radiation. In Phoenix A, two forces are locked in an eternal dance. Gravity, pulling inward, trying to collapse the cluster into a single point, and radiation, pushing outward, resisting that collapse, spreading energy through space. The black hole feeds, and as it does, it radiates. That radiation heats the gas, causing it to expand, but gravity pulls back, compressing the gas, making it dense enough for the black hole to feed again. It's a feedback loop, a cycle that repeats over and over, maintaining a fragile equilibrium. Too much gravity, and the cluster collapses. Too much radiation, and the cluster disperses. But Phoenix A has found the balance. The dance continues, year after year, century after century, a cosmic waltz, performed on the grandest stage imaginable. And we're just beginning to understand the choreography. The magnetic fields that shape the light, woven through the gas of Phoenix A. There are magnetic fields, invisible lines of force, threading through the plasma, guiding the motion of charged particles. These fields are weak compared to Earth's magnetic field, but they're vast, stretching across millions of light years. And they're important. They shape the jets from the black hole, channeling matter and energy along specific paths. They influence the cooling of the gas, preventing it from collapsing too quickly. And they generate light. As electrons spiral along the magnetic field lines, they emit radiation, glowing in radio waves. This is how we see the jets, the bubbles, the structure of the cluster, not through the gas itself, but through the light created by particles dancing along magnetic highways. Phoenix A is a magnetic sculpture, carved from plasma and energy, shaped by forces we can barely detect, the bubbles rising through the hot gas. If you could see Phoenix A in X-rays, you'd notice something strange. The hot gas isn't uniform. There are holes in it, bubbles, cavities, where the gas has been pushed aside, creating voids in the glowing plasma. These bubbles are carved by the black hole's jets. As the jets plow through the gas, they displace it, creating expanding shells of emptiness that rise through the cluster like bubbles in a lava lamp. Slowly, over millions of years, they float outward, growing larger, eventually dispersing into the surrounding medium. But even as they fade, new bubbles form, carved by fresh eruptions from the black hole. It's a continuous process, a cosmic fountain, with bubbles rising and falling over timescales longer than human civilization. And each bubble tells a story, a record of the black hole's activity, written in the fabric of space itself. The cavities carved by invisible power. The bubbles in Phoenix A aren't just empty space. They're cavities carved by one of the most powerful forces in the universe. The jets from the central black hole, though invisible to our eyes, carry immense energy. They push through the surrounding gas like a plow through soil, creating vast hollows in the plasma. These cavities can be thousands of light years across, dwarfing entire galaxies. And they're not static. They're dynamic, expanding, evolving, filled with relativistic particles spiraling along magnetic fields. When astronomers measure these cavities, they can calculate how much energy the black hole has released. The numbers are staggering, enough energy to power entire civilizations for trillions of years, all channeled into invisible jets, carving monuments in the cosmic plasma. Phoenix A's cavities are scars, evidence of the black hole's power, preserved in the structure of the cluster itself, the evidence of ancient outbursts. The bubbles we see in Phoenix A aren't the only ones. There are older structures, farther out, fainter, harder to detect. Evidence of ancient outbursts, eruptions that happened millions or even billions of years ago. These ghost bubbles have been stretched and distorted by the cluster's motion, twisted by gravity, eroded by time. But they're still there, faint shadows in the X-ray glow, whispering stories of the black hole's past. Each outburst represents a cycle of feeding and feedback, a time when the black hole consumed a massive amount of gas, released enormous energy, and then settled down, waiting for the next meal. Phoenix A's history is written in these bubbles, layered like tree rings, each one marking a chapter in the cluster's long life. And by studying them, astronomers can piece together the black hole's biography, a life measured in cosmic eruptions, the echoes of past eruptions. When the black hole erupts, it doesn't just carve bubbles. It sends out waves, pressure waves, sound waves, rippling through the hot gas like echoes through a canyon. These waves are real, not metaphorical. They're oscillations in the density and temperature of the plasma, traveling outward at the speed of sound in the cluster, about 1,000,000 kilometers per hour, slow by cosmic standards, but relentless. These sound waves carry energy, heating the gas as they pass, preventing it from cooling too quickly. And they leave traces, ripples in the X-ray emission, subtle variations in temperature and density that astronomers can measure. Phoenix A is filled with these echoes, layer upon layer, each one a memory of an eruption long past. The cluster hums with the sound of its own history, a deep, inaudible note that's been playing for billions of years. The sound waves that rippled through space. Imagine the deepest note ever played, not in an auditorium, but in space itself. In Phoenix A, the black hole's eruptions create sound waves so low, so deep, that no human could ever hear them. They're pressure waves, oscillations in the hot gas, vibrating at frequencies far below the range of human hearing. In fact, the note produced by the black hole in the nearby Perseus cluster, a similar system, is about 57 octaves below middle C. The deepest note in the universe, Phoenix, likely produces similar sounds. These waves travel through the cluster, heating the gas, stirring it, preventing it from settling into stagnant equilibrium. It's a cosmic symphony, conducted by a black hole, heard by no one, but felt by the entire cluster. A reminder that space isn't silent. It's alive with vibrations, with echoes, with sounds too deep for human ears to catch. The cooling of cosmic plasma. The gas in Phoenix A wants to cool. It radiates energy constantly, losing heat to space in the form of X-rays. And as it cools, it grows denser, more prone to collapse. Left unchecked, this cooling would trigger a catastrophic cascade. More cooling leads to more collapse, which leads to more cooling, until the entire cluster implodes. But that doesn't happen, because the black hole intervenes. Its jets pump energy back into the gas, reheating it, stopping the cooling catastrophe before it can begin. This is called feedback, and it's one of the most important processes in modern astrophysics. Without it, galaxy clusters like Phoenix A would look completely different. They'd be cold, dense, filled with stars instead of hot gas. But feedback changes everything. It regulates the cluster, keeps it balanced, allows it to evolve slowly over billions of years. Phoenix A is a living laboratory for studying this process. The formation of thousands of new suns. Right now, in the center of Phoenix A, stars are being born. Not a few. Thousands, every year. Clouds of gas, cooled just enough to collapse, ignite fusion in their cores, becoming new suns. These stars are massive, bright, burning blue and white, living fast and dying young. They'll only last a few million years before they explode as supernovae, scattering their enriched material back into the gas. But in that brief time, they shine. They light up the galaxy. They add to the glow of Phoenix A, contributing to the radiance that makes it one of the most luminous objects in the universe. This level of star formation is rare, especially in a cluster this massive. Most clusters have long since exhausted their gas, leaving only old, dying stars. But Phoenix A is different. It's still alive, still creating, still burning. The forge of new worlds, hidden in the heart of an ancient cluster. The young stars, hidden in dust. Many of the newborn stars in Phoenix A are hidden, shrouded in thick clouds of dust, invisible to optical telescopes. But dust can't hide them from infrared eyes. Telescopes like Spitzer, and now the James Webb Space Telescope, can peer through the dust, seeing the warm glow of young stars heating their surroundings. What they reveal is astonishing. Clusters of massive stars, still embedded in their birth clouds, glowing fiercely in infrared light. These stars are only a few million years old, babies by cosmic standards, and they're everywhere, scattered throughout the central galaxy, lighting up pockets of dense gas. The dust will eventually disperse, blown away by stellar winds and supernova explosions, revealing the stars beneath. But for now, they remain hidden, a secret population, visible only to those who know where to look. Phoenix A's brightest stars are still waiting to be unveiled. The blue glow of star formation. When astronomers look at Phoenix A's central galaxy in optical light, they see something unexpected, a blue glow, not the red light of old stars which dominates most massive galaxies, but the blue light of young, hot stars. This is the signature of star formation. Massive stars burn blue, radiating enormous amounts of energy in the ultraviolet and visible spectrum, and Phoenix A is full of them. The blue glow is strongest at the center, where the cooling gas is densest, where star formation is most intense. It's a beacon, a signal that something unusual is happening here. Most galaxies, this massive, stopped forming stars billions of years ago. But Phoenix A is different. It's young at heart, still creating, still growing, still glowing with the fire of newborn suns. A blue island in a sea of red, defying the expectations of cosmic old age. The phoenix burning bright again. The name Phoenix isn't just poetic, it's descriptive. Phoenix A is burning, not with literal fire, of course, but with energy, with light, with the fury of creation and destruction intertwined. It burned in the past, and then it quieted, cooling over millions of years. But now, it's burning again. The black hole has found new fuel. The gas is collapsing, forming stars. Energy radiates across the spectrum, from radio waves to X-rays. It's a rebirth, a resurgence, a second coming of the cosmic firebird, and this cycle will continue. Phoenix A will burn, then cool, then burn again, each cycle lasting millions of years, stretching across the lifetime of the universe itself. We're lucky to witness one of these cycles, to see the phoenix in flight, bright, fierce, eternal. The rebirth of a galaxy cluster. In a way, every cycle is a rebirth. Phoenix A doesn't just exist, it transforms, it collapses and erupts, it cools and heats, it consumes and creates. Each cycle leaves it changed, evolved, different from what it was before. New stars are born, adding to the population. Gas is reheated, redistributed, changed in composition. The black hole grows, becomes more massive, alters the gravitational landscape, and the cluster itself, the web of galaxies, bound together by gravity, shifts, reorganizes, evolves. Phoenix A today isn't the same as Phoenix A billion years ago, and it won't be the same a billion years from now. It's a living thing in the sense that it grows, changes, responds to its environment. A galaxy cluster reborn, again and again, across the eons. The phoenix, eternal, flying through time. The scale beyond imagination. Let's talk about scale, because Phoenix A is big. Not just big, but incomprehensibly vast. The cluster spans millions of light years. The central galaxy alone is larger than the Milky Way. The black hole at its core contains billions of solar masses. The gas between galaxies weighs more than all the stars combined, and the energy output, more than 1 trillion suns. These numbers are so large they lose meaning. Our brains aren't built to comprehend scales like this. A light year is already unfathomable. The distance light travels in a year, about 6 trillion miles, and Phoenix A is millions of those. It's a scale beyond human experience, beyond intuition. All we can do is marvel, try to wrap our minds around it. Fail, inevitably, but try anyway. Because that's what makes astronomy beautiful. It humbles us. It shows us how small we are, and how vast the universe truly is. The size of Phoenix, compared to our Milky Way. If you placed our Milky Way galaxy next to Phoenix A's central galaxy, it would look like a coin next to a dinner plate. The Milky Way is about 100,000 light-years across, a respectable size by galactic standards. But Phoenix A's brightest cluster galaxy is several times larger, swollen by billions of years of mergers and growth. And that's just one galaxy. The entire Phoenix cluster spans millions of light-years, containing hundreds of galaxies, each comparable in size to the Milky Way. If you could shrink Phoenix down so the Milky Way fit in your hand, the cluster would stretch across a city. That's the difference in scale. Our entire galaxy, with its hundreds of billions of stars, would be just one small piece of Phoenix A's vast empire. It's humbling. We think of the Milky Way as enormous, and it is. But Phoenix A reminds us that there are structures in the universe so much larger, so much more massive, that our home galaxy is barely a footnote in their story. The weight of 100 trillion suns. How much does Phoenix A weigh? It's a strange question, but astronomers have an answer. About 100 trillion times the mass of our sun, maybe more. That includes everything: the galaxies, the stars, the black holes, the hot gas, and the dark matter that holds it all together. Most of that mass is invisible. Dark matter, a mysterious substance that doesn't emit light but exerts gravity, makes up the bulk of the cluster's weight. We can't see it, but we can measure its effects. The way galaxies move, the way light bends around the cluster, all of it points to an enormous gravitational mass, far exceeding what we can see. 100 trillion suns. It's a number so large it's almost meaningless, but it's real, and it's out there, billions of light years away, pulling space itself into curves and wells, shaping the universe around it. The gravitational power of the cluster. Gravity is the weakest of the fundamental forces, but over cosmic scales, It's the only one that matters. And Phoenix A has gravity in abundance. The entire cluster is held together by it. Hundreds of galaxies, bound in a gravitational embrace that will last for billions of years. That gravity is so strong, it bends light. If you could look at Phoenix A from just the right angle, you'd see distorted images of galaxies far beyond it, their light warped and magnified as it passes through the cluster's gravitational field. Astronomers call this gravitational lensing, and it's one of the most powerful tools we have for studying distant clusters. Phoenix A's gravity reaches across millions of light years, pulling in gas, corralling galaxies, even affecting the motion of neighboring clusters. It's an anchor in the cosmic web, a gravitational titan that shapes everything around it. The galaxies orbiting the giant. Phoenix A isn't just one galaxy. It's hundreds, each one orbiting the central giant, bound by gravity, dancing in slow, stately orbits that take hundreds of millions of years to complete. Some of these galaxies are massive ellipticals, filled with old red stars. Others are spirals, still forming new stars in their disks. And some are small, dwarf galaxies, barely a fraction of the Milky Way's size, caught in the cluster's gravitational net. They all orbit the center, where the brightest cluster galaxy sits, the gravitational heart of Phoenix A. Over time, some of these galaxies will fall inward, merging with the central giant, adding their stars to its growing mass. Others will be ejected, flung out of the cluster by gravitational interactions. It's a dynamic system, constantly evolving, constantly changing, a cosmic dance that's been going on for billions of years. The collisions that built it over time. Phoenix A wasn't born fully formed. It grew, piece by piece, over billions of years, through countless collisions and mergers. Smaller galaxy groups fell into the cluster, their galaxies scattering, their gas heating as they merged with Phoenix A's hot plasma. Each collision added mass, energy, structure. Some mergers were gentle, barely noticeable. Others were violent, triggering starbursts, reigniting the central black hole, sending shock waves rippling through the gas. And with each collision, Phoenix A grew larger, more massive, more complex. This is how all galaxy clusters form, through hierarchical assembly, small structures merging into larger ones. But Phoenix A is special because we can still see the evidence of recent mergers, the disturbed gas, the off-center bubbles, the rapid star formation. Phoenix A is still being built. The construction continues, even now, billions of years after it began. The cannibalism of smaller galaxies. At the center of Phoenix A, the brightest cluster galaxy, is a cannibal. It doesn't hunt, exactly, but it consumes. Smaller galaxies that wander too close are torn apart by tidal forces, their stars stripped away, absorbed into the central giant's growing mass. This process is called galactic cannibalism, and it's common in galaxy clusters. The central galaxy sits at the bottom of the gravitational well, slowly devouring everything that falls in. Over billions of years, it's consumed dozens, maybe hundreds of smaller galaxies. Each one adds to its mass, making it larger, more massive, more dominant, and the process continues. Right now, there are galaxies falling toward the center, doomed to be consumed, their stars becoming part of the central giant. It's not violent, not dramatic, just slow, inevitable. The cosmic food chain playing out over timescales longer than the age of our sun. The merging of cores and black holes. When two galaxies merge in Phoenix A, their stars mix, their gas collides, and their central black holes spiral toward each other. This is one of the most dramatic events in the universe. Two supermassive black holes, each weighing millions or billions of solar masses, orbiting each other in an ever-tightening dance. As they spiral inward, they emit gravitational waves, ripples in space-time itself, carrying energy away from the system. Eventually, they merge, combining into a single, even more massive black hole. And when they do, They release a burst of gravitational radiation so powerful it could be detected across the universe. This is how Phoenix A's central black hole grew so large. Through merger after merger, black hole after black hole, over billions of years, and it's still growing. Somewhere in Phoenix A, right now, black holes are spiraling toward the center, destined to merge, adding to the mass of the monster at the core. The cosmic tides of the Phoenix cluster. Everything in Phoenix A is subject to tides, not the familiar ocean tides of Earth, but gravitational tides, the stretching and squeezing caused by differences in gravitational force. Galaxies on one side of the cluster feel a slightly different pull than those on the other side, causing them to elongate, distort, sometimes tear apart. Gas clouds are stretched into filaments, pulled into streams that feed the central black hole. Even stars within galaxies feel these tides, though they're usually strong enough to hold themselves together. These cosmic tides shape the structure of Phoenix A, creating streams of matter, shells of stars, asymmetries in the gas distribution. They're subtle, often invisible, but they're always there, constantly reshaping the cluster, sculpting it over millions of years. Phoenix A is a dynamic system, molded by gravity's invisible hands, the gas that never cools completely. One of the mysteries of Phoenix A is the gas. It should have cooled by now. It's been radiating energy for billions of years, losing heat to space by all rights. It should have collapsed, formed stars, left nothing but a cold, dead cluster, but it hasn't. Because every time the gas starts to cool too much, the black hole intervenes. Its jets pump energy back in, reheating the plasma, stirring it, keeping it dynamic. It's a balancing act, and Phoenix A has mastered it. The gas is hot, but not too hot. It's cooling, but not too fast. It's forming stars, but not depleting itself. This state of near equilibrium is rare, delicate, and beautiful. Most clusters either cool too much or stay too hot. Phoenix A sits right in the middle, a Goldilocks zone of cosmic thermodynamics. The gas that never cools completely, always on the edge of collapse, always pulled back from the brink. The constant cycle of destruction and renewal. Phoenix A doesn't just exist, it cycles, destruction and renewal, feeding and feedback, cooling and heating, all happening simultaneously, continuously, endlessly. Gas cools and collapses, forming stars. Stars explode as supernovae, reheating the gas. The black hole feeds, launching jets that carve the plasma. The jets fade, the gas cools again, and the cycle repeats. It's been happening for billions of years. It will continue for billions more. This is the heartbeat of Phoenix A, the rhythm that keeps it alive. And it's not unique to this cluster. We see similar cycles in other systems, smaller and less dramatic, but following the same pattern. Creation requires destruction. Growth requires loss. Phoenix A embodies this cosmic truth, a monument to the eternal cycle of change that governs the universe. The role of dark matter in its growth. Beneath everything we can see in Phoenix A, there's something invisible, dark matter, a mysterious substance that makes up most of the cluster's mass, but doesn't emit light, doesn't interact with normal matter, except through gravity. We don't know what it is. We've never detected it directly, but we know it's there because we can see its effects. The galaxies in Phoenix A move too fast to be held together by visible matter alone. Light bends around the cluster more than it should. The gas is hotter than it would be without extra gravitational mass. All of this points to dark matter, an invisible scaffold that holds Phoenix A together. Without it, the cluster would fly apart, scattering into the void. Dark matter is the foundation upon which Phoenix A is built, the hidden architecture of the cosmic web, the web that holds the cluster together. Zoom out far enough, and you'll see that Phoenix A isn't isolated. It's part of a vast cosmic web, a network of dark matter filaments that span the universe. These filaments are invisible, but they're there, connecting clusters, guiding the flow of gas, shaping the large-scale structure of everything. Phoenix A sits at a node in this web, where multiple filaments intersect. That's why it's so massive. Material flows along the filaments, funneled toward the cluster, adding to its mass over time. This web formed early in the universe's history, shaped by tiny density fluctuations in the Big Bang's aftermath. Over billions of years, those fluctuations grew, pulling matter together, forming the cosmic web we see today. Phoenix A is a knot in that web, a concentration of matter and energy, held in place by dark matter's invisible threads, the invisible scaffolding of the universe. Dark matter is more than just mass. It's structure. It forms the scaffolding upon which everything else is built. Without it, galaxies wouldn't have formed, clusters wouldn't exist, stars, planets, life itself would never have come to be. Dark matter pulled the first wisps of hydrogen together, creating the seeds of the first stars. It guided the formation of galaxies, clustering them into groups and clusters. It carved the cosmic web, creating the universe's large-scale structure. Phoenix A owes its existence to dark matter. The visible components, the galaxies, the gas, the black hole, are all just window dressing. The real structure, the foundation, is invisible. Dark matter is the universe's hidden skeleton, and Phoenix A is built upon it. We may never see it directly, but we can see what it creates, and that's enough. The expansion of space itself. While Phoenix A is held together by gravity, the universe around it is expanding. Space itself is stretching, pulling distant galaxies away from each other at ever-increasing speeds. This expansion is driven by dark energy, another mysterious component of the universe that we don't understand, but it's real. We can measure it in the redshift of distant galaxies, in the dimming of distant supernovae, and it affects Phoenix A. The cluster itself isn't expanding. Gravity holds it together, but the space around it is stretching. Distant clusters are receding, carried away by the expansion, moving faster and faster the farther away they are. Eventually, in the far future, Phoenix A will be isolated, surrounded by empty space, the only structure visible in an expanding void. But that's trillions of years away. For now, Phoenix A remains connected to the cosmic web, part of the universe's grand structure. The Phoenix cluster as a window into the past. When we look at Phoenix A, we're not seeing it as it is today. We're seeing it as it was billions of years ago. Light takes time to travel, and Phoenix A is so far away that its light has been traveling for a significant fraction of the universe's age. We're looking back in time, seeing the cluster as it was in the early universe, when galaxies were still assembling, when black holes were growing rapidly, when star formation was at its peak. Phoenix A is a time machine, a window into cosmic history. By studying it, astronomers learn about how clusters form, how galaxies evolve, how black holes and star formation interact. Every observation adds to our understanding of the universe's past, helping us piece together the story of how we got here. Phoenix A is ancient light, carrying ancient stories, the light that traveled billions of years. The light we see from Phoenix A began its journey long before humans existed, before Earth formed, before the sun ignited. It's been traveling through space for billions of years, crossing vast distances, passing through cosmic voids, threading its way through the expanding universe. And finally, after all that time, it reaches us, captured by telescopes, analyzed by instruments, turned into images and data. That light carries information. The spectrum tells us about the gas composition. The X-rays reveal the temperature. The redshift shows us the distance. Every photon is a messenger, carrying news from across the cosmos. And when we receive that light, we're connecting with the distant past, touching something that happened incomprehensibly far away and long ago. Phoenix A's light is a gift, a window into the universe's history, the ancient glow of the early universe. Phoenix A exists in what astronomers call the early universe, though early is relative. The universe is about 13.8 billion years old, and Phoenix A formed several billion years ago when the universe was younger, denser, more active. Back then, galaxy formation was at its peak. Clusters were assembling. Black holes were feeding voraciously. Star formation rates were higher than they are today. Phoenix A is a relic from that era, a survivor, still active, still glowing. When we study it, we're learning about conditions in the early universe, about how structures formed when the cosmos was in its youth. The cluster's light is ancient, but the processes it reveals are fundamental, timeless. By understanding Phoenix A, we understand cosmic evolution itself, the redshift that reveals its distance. How do we know how far away Phoenix A is? Through redshift. Through redshift, as light travels through the expanding universe, its wavelength stretches, shifting toward the red end of the spectrum. The more space expands, the more the light is redshifted. By measuring this shift, astronomers can calculate distance. Phoenix A has a significant redshift, indicating it's billions of light years away. The exact distance depends on the cosmological model, but it's far, very far. Too far for any spacecraft to reach, even traveling at light speed. Too far to see in detail, without the most powerful telescopes. But not too far to study. Modern instruments can capture Phoenix A's light, analyze it, extract information. Redshift is a cosmic yardstick, and it tells us that Phoenix A is one of the most distant, most ancient structures we've studied in detail. The look back in cosmic time. When you look at something distant, you see it as it was in the past. Look at the sun, and you see it as it was 8 minutes ago, the time it takes light to reach Earth. Look at the nearest star, and you see it as it was 4 years ago. Look at Phoenix A, and you see it as it was billions of years ago. This is what astronomers call look-back time. The farther you look, the further back you see. Phoenix A exists in our past, frozen at a moment billions of years ago. Since then, it's continued to evolve, to change, to grow, but we'll never see that. We're stuck looking at ancient light, watching a movie that's billions of years out of date. It's strange, beautiful, and humbling. Phoenix A as it exists right now, at this very moment, is unknowable. All we have is the past, the universe. When Phoenix A was born, when Phoenix A formed, the universe was different, younger, denser, galaxies were closer together, collisions were more common, and star formation was more vigorous. The cosmic microwave background, the afterglow of the Big Bang, was slightly warmer. Dark energy was less dominant, and the universe's expansion was slower. It was an era of cosmic assembly, when the largest structures were still coming together, when clusters like Phoenix A were being built through countless mergers. The universe was busier then, more active, more violent. Phoenix A is a product of that era, forged in the crucible of the early cosmos, and by studying it, we get a glimpse of what conditions were like back then, billions of years before our sun, our planet, our species existed. The story of galaxies coming together. Phoenix A's story is, at its heart, a story of galaxies coming together. Drawn by gravity, they fell toward a common center, colliding, merging, forming ever larger structures. Each collision brought gas, stars, dark matter, and black holes together, building the cluster piece by piece. This process continues today. Phoenix A is still growing, still accreting material, still pulling in galaxies from its surroundings, and it will continue for billions of years. Eventually, Phoenix A will become even more massive, even more dominant, perhaps merging with other clusters to form a supercluster. This is hierarchical structure formation. the way the universe builds its largest objects, starting small, growing through mergers, assembling over cosmic time. Phoenix A is a chapter in that story, a snapshot of a cluster in mid-construction, still active, still evolving, the era of the first giants. Phoenix A represents an important era in cosmic history, the era of the first giants. Before Phoenix A, there were smaller structures, galaxy groups, protoclusters, the seeds of what would become massive clusters. But Phoenix A is fully formed, a mature cluster, one of the largest and most energetic of its time. It marks a transition from the chaotic early universe to the more organized, structured cosmos we see today. In Phoenix A's era, the first truly massive black holes were forming, the first giant elliptical galaxies were assembling, and the cosmic web was beginning to take shape. Phoenix A is a pioneer, a trailblazer, one of the first of its kind, and by studying it, we learn about how the universe transitioned from small structures to large ones, from simplicity to complexity. The fueling of the central black hole, the black hole at Phoenix A's center, needs fuel. Constantly. Without it, the jets would fade, the feedback would stop, and the cluster would change dramatically. So where does the fuel come from? From the gas around it. The hot plasma that fills the cluster is slowly cooling, slowly falling inward, feeding the black hole. But there's more. When galaxies merge with the central giant, they bring their own gas, adding to the fuel supply. Stars that wander too close are torn apart, their material funneled into the accretion disk. Even the black hole's own jets play a role, stirring the gas, creating density fluctuations that eventually fall back in. It's a self-sustaining system, a feedback loop, where the black hole's activity creates the conditions for its own continued feeding. As long as there's gas in the cluster, the black hole will feed, and Phoenix A has plenty of gas. The feedback loop of energy and matter. Phoenix A is defined by feedback. The black hole feeds on gas, releasing energy. That energy heats the surrounding plasma, preventing it from cooling too quickly. But some gas cools anyway, forming stars which eventually explode, adding more energy back into the system. And some gas cools enough to feed the black hole again, restarting the cycle. It's a loop, with energy and matter flowing in circles, constantly being recycled, redistributed, transformed. This feedback is what keeps Phoenix A in balance. Without it, the cluster would either collapse into a starburst, using up all its gas in a brief, violent burst, or it would stay hot forever, never forming new stars. But with feedback, it can do both. It can be active without destroying itself. Phoenix A is a masterclass in cosmic self-regulation, a system that has learned to sustain itself over billions of years. The jets that prevent the cooling catastrophe. Imagine what would happen if the black hole's jets stopped. The gas would cool unchecked, collapsing toward the center, forming stars at an incredible rate. Within a few 100 million years, the cluster would run out of gas, leaving nothing but a massive galaxy filled with old stars and a dormant black hole. This is called the cooling catastrophe, and it's what theorists predicted would happen in massive clusters. But it doesn't, because the jets prevent it. They pump energy into the gas, heating it, stirring it, keeping it dynamic. The jets are Phoenix A's thermostat, regulating the temperature, maintaining equilibrium. Without them, the cluster would burn itself out. With them, it can last for billions of years, cycling through phases of cooling and heating, destruction and renewal. The jets are the key to Phoenix A's longevity, the secret to its eternal flame. The radio signals from the cluster core. Phoenix A doesn't just glow in X-rays, it also emits radio waves, powerful signals coming from the cluster's core. These radio waves are generated by the black hole's jets, by electrons spiraling along magnetic field lines at nearly the speed of light. The radio emission traces the structure of the jets, showing us where they're going, how they're interacting with the surrounding gas. When astronomers first discovered Phoenix A, it was through these radio signals. They stood out, bright and clear, a beacon in the radio sky. Even today, radio telescopes around the world point at Phoenix A, studying the jets, mapping their structure, measuring their energy. The radio signals are a window into the black hole's activity, a way to see the invisible, to trace the flow of energy from the core to the outskirts of the cluster. The view through the Chandra X-ray Observatory. One of the most important tools for studying Phoenix A is the Chandra X-ray Observatory, a space telescope launched in 1999. Still operating today, Chandra sees the universe in X-rays, revealing the hot gas that fills galaxy clusters. When Chandra looks at Phoenix A, it sees a glowing halo of plasma, brighter at the center where the gas is hottest and densest. It sees the bubbles carved by the black hole's jets, the cavities where gas has been pushed aside. It sees the cooling filaments, streams of gas condensing out of the hot medium. Chandra's observations have been crucial to understanding Phoenix A. They've revealed the energy balance, the star formation, the black hole's power. Without Chandra, Phoenix A would still be a mystery. With it, we've turned the cluster into a laboratory, a place to test theories, to learn how the universe works. The optical glow, captured by Hubble, while Chandra sees X-rays. The Hubble Space Telescope sees visible light, and when Hubble looks at Phoenix A, it sees galaxies, hundreds of them, scattered throughout the cluster, each one a collection of billions of stars. At the center, Hubble reveals the brightest cluster galaxy, glowing with the light of old and young stars mixed together. It sees the blue glow of star formation, proof that new suns are being born. It captures the fine details, the structure of the galaxies, the streams of stars pulled out by tidal forces. Hubble's images complement Chandra's, showing us the stellar component of Phoenix A, the part we can relate to most directly. Because stars are something we understand, we have one overhead every day, and seeing stars in Phoenix A, billions of light years away, connects us to that distant place in a way nothing else can. The infrared secrets, revealed by Spitzer. The Spitzer Space Telescope, which operated from 2003 to 2020, saw the universe in infrared light. And infrared is perfect for studying dust and star formation. When Spitzer looked at Phoenix A, it saw the heat, warm dust, heated by young stars still embedded in their birth clouds. Infrared light pierces through the dust that blocks optical telescopes, revealing the hidden star formation happening at the cluster's core. Spitzer's observations showed that Phoenix A is forming stars even more rapidly than optical observations suggested. Much of the activity is hidden, shrouded in thick dust, visible only in infrared. These observations filled in a missing piece of the puzzle, showing us that Phoenix A's star formation isn't just happening, it's happening at an extraordinary rate. Spitzer's infrared eyes revealed secrets that visible light alone could never show. The new insights from the James Webb Telescope. And now, we have the James Webb Space Telescope, the most powerful observatory ever built. Launched in 2021, Webb sees the universe in infrared with unprecedented clarity. It's only just beginning to study Phoenix A, but the results are already remarkable. Webb can see finer details than Spitzer ever could, resolving individual star clusters, mapping the distribution of dust with precision. It can analyze the spectrum of light, determining the chemical composition of the gas, the age of the stars, the conditions in the cluster. Webb is revealing Phoenix A in ways we've never seen before, peeling back layers of mystery, showing us the cluster in extraordinary detail. And this is just the beginning. As Webb continues to observe, we'll learn even more, uncovering secrets that have been hidden for billions of years. The fine structures of gas and dust. With Webb's help, astronomers are now seeing the fine structures within Phoenix A, filaments of cool gas, threading through the hot plasma, like veins, knots of dust, concentrated in the densest regions, glowing faintly in infrared, shells and arcs of material, shaped by stellar winds and supernova explosions. These structures are small, by cosmic standards, but they're important. They show us where star formation is happening, where gas is cooling, where the black hole's energy is being deposited. They reveal the complexity of Phoenix A, showing that it's not just a uniform blob of hot gas, but a structured, dynamic system with layers upon layers of detail. Every new observation reveals more structure, more complexity, more beauty. Phoenix A is not simple. It's intricate, rich, endlessly fascinating. The temperature of the intracluster medium, the gas between galaxies in Phoenix A, is called the intracluster medium, and it's hot, not warm. Hot, tens of millions of degrees Celsius. At those temperatures, atoms are stripped of their electrons, existing as a plasma, a soup of charged particles. The gas glows in X-rays because of this heat, but the temperature isn't uniform. Near the center, where the black hole's influence is strongest, the gas is hotter, heated by the jets and the radiation from the accretion disk. Farther out, it's cooler, more relaxed. And in some regions, the gas is cooling rapidly, condensing into filaments where the temperature drops below 1,000,000 degrees. These temperature variations tell us about the energy flow in the cluster, about how the black hole's power is distributed, about where star formation is likely to occur. Temperature is a key diagnostic, a window into Phoenix A's inner workings. The hidden filaments of cold gas. Within Phoenix A's hot plasma, there are pockets of cold gas, filaments, streams, clouds of material that have cooled below the temperature of the surrounding medium. These filaments are invisible to X-ray telescopes, but they glow faintly in optical and infrared light. They're important because they're where stars form. When gas cools enough, it can collapse under its own gravity, fragmenting into clumps that eventually ignite fusion. The filaments are the nurseries of Phoenix A, the birthplaces of new stars. They form where the cooling is most efficient, where the black hole's heating is weakest, where conditions are just right for collapse. Astronomers are still mapping these filaments, trying to understand how they form, how they survive in the hostile environment of hot plasma, and how they feed the ongoing star formation at the cluster's core. The unexpected birth of thousands of stars. The sheer number of stars being born in Phoenix A is unexpected, thousands every year. In a galaxy cluster, this massive star formation should have stopped billions of years ago. The gas should be too hot, too dispersed, too agitated by the black hole's energy. And yet, stars are forming. This defies the standard models, the predictions that astronomers had made based on observations of other clusters. Phoenix A is an outlier, a place where the usual rules don't apply, or maybe a place where we're finally seeing the rules in their full complexity. The stars being born here are a surprise, a puzzle, and a gift. They give astronomers a chance to study star formation in an extreme environment, to understand how stars can be born even when every force in the universe seems aligned against them. The phoenix that defies the cosmic rules. Phoenix A is a rebel. It doesn't follow the expected patterns. It forms stars when it shouldn't. It feeds its black hole without destroying itself. It maintains a balance that most clusters can't achieve. It's too bright, too energetic, too active, and that's what makes it so valuable, because the universe isn't always neat. It doesn't always follow our models, our predictions, our theories. Sometimes it surprises us, and when it does, we learn. Phoenix A is teaching us that galaxy clusters are more complex than we thought, that feedback isn't simple, that the interplay between black holes, gas, and star formation can create outcomes we never imagined. Phoenix A defies the cosmic rules, yes, but in doing so, it shows us that the rules themselves need to be rewritten. The questions astronomers still can't answer. Despite decades of study, Phoenix A still holds mysteries. How did it form so quickly? Why is its star formation rate so high? How does the black hole maintain such a delicate balance between heating and cooling? What triggers the jets? And what determines their power? How will Phoenix A evolve in the future? Will the star formation continue, or will it eventually stop? These questions remain unanswered, not because astronomers aren't trying, but because the universe is complicated. Every answer leads to new questions. Every observation reveals new puzzles. Phoenix A is a reminder that we're still learning, still exploring, still discovering. There's so much we don't know, and that's not a failure. It's an invitation to keep looking, keep wondering, keep asking the theories that try to explain its energy. Astronomers have proposed many theories to explain Phoenix A's extraordinary energy output. Maybe it's in the middle of a major merger, two massive clusters colliding, triggering a burst of activity. Maybe the black hole recently swallowed a smaller companion, doubling its mass overnight. Maybe the cooling flow is unusually strong, funneling more gas toward the center than in typical clusters. Maybe the magnetic fields are aligned in a way that makes the jets more efficient. Or maybe Phoenix A is just a statistical fluke, a 1 in a billion combination of circumstances that happen to create something spectacular. We don't know which theory is correct. Maybe all of them contribute, maybe none of them do. But the theories give us a framework, a way to test ideas, to make predictions, to design new observations. Phoenix A challenges our theories, and that's how science moves forward. The connection between black holes and galaxies. Phoenix A is a laboratory for studying one of the most important relationships in astrophysics, the connection between black holes and galaxies. Across the universe, we see a pattern. The mass of a galaxy's central black hole is tightly correlated with the mass of its central bulge. Bigger galaxies have bigger black holes. But why? How do they know about each other? The black hole is tiny compared to the galaxy, and yet they're linked. Phoenix A offers clues. The black hole's feedback regulates star formation, shaping the galaxy's growth, and the galaxy's mergers feed the black hole, allowing it to grow. They co-evolve, each influencing the other, locked in a cosmic partnership. By studying Phoenix A, astronomers are learning how this partnership works, how black holes and galaxies grow together, how one shapes the other. It's a fundamental question in astronomy, and Phoenix A is helping us answer it. The clues about how the universe evolves. Phoenix A isn't just interesting in its own right. It's a clue to how the entire universe evolves. Galaxy clusters, like Phoenix A, are the largest bound structures in existence. They represent the endpoint of cosmic structure formation, the culmination of billions of years of gravitational assembly. By studying Phoenix A, we learn about that process. How do clusters form? How do they grow? How do black holes, gas, and star formation interact over cosmic time? The answers to these questions apply, not just to Phoenix A, but to all clusters, all galaxies, all structures. Phoenix A is a window into cosmic evolution, a single example that illuminates the whole. Every observation, every measurement, every discovery contributes to our understanding of how the universe came to be the way it is. Phoenix A is a piece of the puzzle, and we're slowly figuring out where it fits. The beauty of order in chaos. There's something beautiful about Phoenix A, not just in the images, though they are stunning, but in the underlying order, the chaos of colliding galaxies, erupting black holes, exploding stars, all somehow balancing into a stable, functioning system. It's like a symphony, where 100 different instruments play different parts, but together they create harmony. Phoenix A is chaotic, yes, but it's also ordered. The feedback loops, the energy flows, the cycles of cooling and heating, they all work together, creating something greater than the sum of its parts. It's a reminder that the universe, despite appearances, has structure, patterns, rules, and even in the most extreme environments, in the most energetic objects, there's a beauty to be found. an elegance in the way things work, order emerging from chaos, the symbolism of a reborn galaxy. The phoenix, in mythology, is a symbol of hope, of renewal, of the idea that endings are not final, that from the ashes of destruction, new life can emerge. Phoenix A carries that symbolism. It's a galaxy cluster that has died and been reborn, not once but many times, over billions of years. Each cycle of cooling and heating, each burst of star formation, each eruption of the black hole is a kind of rebirth. Phoenix A doesn't just exist. It transforms, it renews itself, it endures. And in a universe governed by entropy, where everything tends toward decay and dissolution, that's remarkable. Phoenix A is a symbol of resilience, of life's ability to persist, to adapt, to rise again. A cosmic phoenix, burning bright, refusing to fade, the fire that never truly dies. In the old stories, the phoenix's fire never goes out. It burns, dims, and then ignites again, an eternal cycle. Phoenix A is the same. Its fire, the energy from the black hole, the light from new stars, the glow of hot gas, has been burning for billions of years, and it will continue. Maybe not forever. Eventually, the universe's expansion will isolate Phoenix A, cutting it off from new fuel. The black hole will exhaust its food supply. The stars will age and die. The cluster will cool, darken, fade. But that's trillions of years away. For now, and for the foreseeable future, Phoenix A burns. Its fire is not eternal in the absolute sense, but by human standards, by the standards of civilizations and planets and even stars, it might as well be the fire that never truly dies, a flame in the cosmic darkness, burning now, burning still, the eternal flight of the phoenix. And so Phoenix A flies on, not through space, exactly. It's bound by gravity, anchored to its place in the cosmic web, but through time. It's been flying for billions of years, evolving, changing, transforming with each passing epoch, and it will continue to fly. Long after our sun has died, long after Earth is gone, long after the last human thought has faded into silence, Phoenix A will still be there, glowing in the darkness, a testament to the universe's power and beauty. Its flight is eternal, in the sense that it transcends any single moment, any single observation. We see it as it was billions of years ago. Future observers, if any exist, will see it as it will be billions of years from now. Different, perhaps unrecognizable, but still Phoenix A, still flying, still burning, the eternal phoenix, soaring through the cosmos, carrying its fire across the ages.